Hi there, welcome to the fourth part of the tutorial how to play a video on Arduino Uno. We finally arrived to our first milestone of this project. In fact, in this episode we will show you how to play an unlimited length animation stored on the SD card. Let's go for the next hack! Last time we analyzed the SPI and USART in SPI mode connections, and we showed that the USART allows for a much higher transfer rate. This was a crucial point. In fact, when dealing with videos, one must find a trade-off between computational power and bandwidth or memory usage. However, an Arduino Uno has almost no computational power to perform even the simplest on-the-fly decoding at 20 frames per second. Therefore, the video must be stored in the RAW format, i.e. without any compression. Let's do the math. A 160 by 128 frame will take 40 kilobytes at 16 bits per pixel. At 20 frames per second, this means more than 800 kilobytes per second. That's huge. However, the price per gigabyte is nowadays very small, and the 4 GB SD card can store about 80 minutes. There is still another problem: the bandwidth. In fact, 800 kilobytes per second is much larger than what we achieved last time with the USART. We already said in the previous video that the throughput can be improved by reading more than one sector at once. However, other two problems arise. First, the Arduino Uno has just 2 kilobytes of RAM, and the FATFS library alone already takes roughly 600 bytes, leaving space only for less than 3 sectors. Second, we must then send the data we read from the SD card to the display using the same USART. Therefore, the total system bandwidth would be 1.6 megabytes per second, and not just 800 kilobytes per second. However, since we do not need to perform any computation on the video data, such data doesn't even have to enter the CPU. And this is what we are going to do. Instead of transferring the data from the SD to the CPU and from the CPU back to the display, we can just connect the SD output line to the display input line. In this way, by enabling the display when the SD card is actually outputting video data, we can directly transfer the video data from the SD card to the display. This resembles the Direct Memory Access technique, as known as DMA. The only problem of this solution is that with such a connection, the CPU can never access the display to properly initialize it. A quick workaround is to use a multiplexer and have another GPIO pin to select where the display data input line is connected to, the CPU or the SD card. But wait, another IC, another GPIO? We are from next hack, aren't we? We must find a much clever solution. A resistor. Let's explain how does it work. Let's suppose for a moment that we are working on a 3.3 volt system. In this way, no level translation is necessary. When only the SD card is selected, the SD is directly connected to the CPU. The resistor does not interfere, because the logic level on MISO is forced by the SD card, and the logic level on MOSI is forced by the CPU. If these two levels are different, nothing will occur. A current will flow from one line to the other. But if the resistor value is large enough, the current will be small enough not to create any problem. When only the display is selected, the SD card releases the bus. Therefore, its data out signal, the out, will be in high impedance. In other words, it will act as if it were disconnected. Data from the CPU will pass through the resistor to the display DIN line. If we select both the display and the SD card, magic occurs. In fact, the SD card is still directly connected to the CPU, as in the first case. However, the display is also listening to the SD card and not to the CPU. In fact, the external resistor will have a much larger value with respect to the output of the SD card. In this way, the logic level read by the display will be determined by the SD card and not by the CPU. Perfect! We just need a resistor. Well, not just one. In fact, we have another problem. The Arduino Uno works at 5 volts. Therefore, we need 5 volt to 3.3 volt level translators, as we did in the second video of this series. The values of all the resistors must be carefully chosen to meet bandwidth and voltage levels specifications. In our website you'll find all the detailed calculation of all the resistor values. Here is the final schematic. Since our circuit gets now quite messy, we prefer to build it using a prototyping board instead of a breadboard. Remember, you must use the hacked version of the display, as we did in the second video. We used KiCad to lay out the connections in order to simplify the soldering process. Soldering the circuit is very easy. The only trick is to press the headers as shown here. We also suggest to first solder the resistors and the connectors, then trim the resistors wires and use them as the connections. This completes the hardware. Let's now deal with the software. First of all, we need to create some functions that select the display when the SD card is outputting data. We created a copy of the function fread on the FATFS library and we modified it. In such function, we see that it calls another function named diskRead. Therefore, we copy and modify this function too. DiskRead in turn calls RCVR data block. So let's copy and modify this function. Yes, again another function is called RCVR SPI multi. We must copy it too. Finally, this is the function we were looking for. We modify it in order to select the display before reading the sector and deselect it after completion. The main program now gets simple. In the setup function we put everything we need to prepare the display for drawing data. In the first part of the loop function we open a file named video.raw. Then we create another loop in which we read large chunks of data using the new function we created. We read 40 kilobytes at once, but we do not use any buffer as we do not need to store the data. In this way we amortize all the overheads we discussed about in the previous video. The loop exits when there are no data bytes available left. The only limit of the video length is the SD card size. Now everything is ready and we just need a video in the RAW format. For this purpose we need to perform 2 steps. As a first step, export your video as a collection of bitmap pictures. The resolution of each picture must be 160 by 128 with 24 bits per pixel. The original video must have a frame rate of 20 frames per second. If your video has a different frame rate, you can change it during the export process. In our website we explain everything to do this. Then use the command line tool available on our website to create a single big file from all the frames. In nexthack.com you will find both the program and the full source code. The code can be also compiled for Linux or Mac. Now put the created file on the SD card. Upload the sketch to the Arduino and put a jumper in the position we are now showing. This will prevent the programming IC from interfering with the SD card and the display. Remember to remove the jumper and disconnect the shield when you want to upload again your sketch. After this, turn off the Arduino, insert the shield you have created and connect the Arduino again. After some while, you'll see the video playing. However, for sure, it won't play at 20 frames per second. It will likely play faster, as we did not put any synchronization. To do this, simply uncomment the line synchronized to 20 Hz. The frame rate can be measured using a scope or a frequency meter on the chip select line of the display. You will measure a frequency which is 80 times the frame rate, as one frame is composed of 80 sectors. We got 1.71 kHz without synchronization, which corresponds to about 21.4 frames per second. That is 855 kilobytes per second, which is very close to the theoretical maximum value one could achieve using an 8 MHz USART. The code without synchronization is a useful tool to assess how much headroom we have left for the audio. For best performance, we recommend using a large cluster size. For instance, we used 16 kilobytes clusters. The card access time will also play a major role on the maximum speed. What speed did you get? Write a comment. If you uncomment the line synchronized to 20 Hz, you will achieve exactly 1.6 kHz. That is, your video is playing at 20 frames per second. That's all for today. No, wait, where is the magic box? We promised we would have shown what's inside, but there is no magic box. Well, if you look closer, actually there is a magic box. The 680 ohm resistor is the magic box. It acts like a DMA controller, allowing for the data to go to the right place. Now really, that's all for today. In the next episode, we will show you how to play a 16-bit audio file. This will be required for the last step, integrating audio and video. This won't be trivial, and further optimization will be needed. As always, you'll find everything you need for this project in our website, next-hack.com. Please rate, comment, share and subscribe. Thanks for watching. What's your next hack?